I've got two of these multi-way adapters that come from different places. So this one here I got from a supermarket a few weeks ago, can't remember which, but the brand on it is Jackson, and this is the IKEA one, and both of these have got the integrated USB ports, and that turns out to be quite handy because so many things need recharging these days, so I quite like the idea of these. But when you come to plug in the iPad, you find an interesting difference. So if I do the Jackson device first, so that's drawing 0.89, so let's say getting on for 1 amp. So it's not really charging at its maximum. If we have a look at the iPad, you'll see it's at 57%, so it really does need charging at the moment. So only 1 amp with the Jackson one. With the IKEA one, if we plug in the IKEA one, look at that, it just races right up to 2.2 amps. That's dropped off a little bit now, but so it's close to 2 amps it's drawing. So this is really using the maximum power available, which will, you know, greatly shorten the charging time for the iPad. So why are these different? This is the question. Why do these two on the surface very similar products behave differently? I'm going to try and answer that. So if we compare this with a USB hub, so this is a USB hub with 4 ports, and if I plug in the iPad into here, what we see is, so it's charging at less than half an amp, so you've got 400 or so milliamps. Because with standard USB ports, devices are not supposed to draw more than half an amp, because a hub port is not necessarily a charging port, it's a device port. And by way of further comparison, I've got one of these Poundland USB adapters, and this is one of the ones that Big Clive took apart in a show of his a while back, and I'll put a link to that down below because it's quite interesting. He breaks it open and we get to see the circuitry. So if we plug that in, plug in the iPad again, so again 0.89, so it's charging at only 1 amp. And if we look at the specifications on here, this one says that it can supply up to 1500 milliamps, and I think Clive showed that it could do that. So why are all these chargers different? Well, let me try and explain. The USB plug has 4 connectors in it, and you have +5 volts and 0 volts, which are the main power pins, and you also have these pins called D- and D+. Now the idea of these center pins here are so that when you use USB as a communication device, so for example when you plug in your printer to a computer via USB, these pins here are where the data is actually being exchanged. So you have the data going actually through those 2 pins. But these pins are also used when the device is being plugged into a power pack, so a wall wart or a charger of some kind. And then the D+ and the D- pins are actually used to signal what the capabilities of the charger are. So if you look at a normal USB port, what you see inside there is you've got 5 volts, you've got 0 volts, and then say that the device is being plugged in at this end here, this end. So what happens normally is that the D- and the D+ these are both connected to ground, like so, by a 15k resistor. So this means that the device that you've plugged in here, by looking at the D- and the D+, you can see that both these are set to 0, and if it were a sophisticated type of device, it would actually be able to measure the resistance between that pin and ground, and it would know that this is a standard data port. However, there are various methods that have evolved so that the charger can tell you whether it is capable of producing a lot of current, because in this SDP mode, the most current that you can get flowing through here is 500 milliamps. So the specification is set to protect the USB port so that you can't burn the USB port out by connecting a device to it. But with a charger, what you have is you want to be able to supply 1 amps or 2 amps of power using that port, and the way they do that depends on the kind of device that you're looking at. So first of all, there's a specification called DCP, and what happens in DCP is the D- and the D+ are simply looped to each other inside the charger, which means that when you plug a device in, it can put a voltage in here and it can measure the voltage on there, and if they're the same, then it knows that these are looped back, and it takes that as a signal to say that a high amount of current will be available and it will draw more current. However, this DCP specification, while many devices understand it, the Apple devices don't understand it, because what's happening inside an Apple device is you have the 5 volts, again 0 volts, D- and D+, and in order to specify that this is a high current charger, you have to the charger has to present 2.7 volts here and 2.7 volts here. So the iPad, when you plug it in, is looking for the 2.7 and 2.7 on these pins, and if it doesn't see it, it will refuse to draw a lot of current. So what we can conclude from the devices that we looked at is that the IKEA one looks like this, where the Jackson multi-way adapter probably looks like this, and we'll be able to measure that using a multimeter, and I'll do that in a moment. So often inside the iPad chargers, what you see is actually a little resistive network, in fact. So they put a couple of resistors between 5 volt and ground, like so. One goes to the D+ and one goes to the D-. So this resistive divider can present a voltage on these pins. Now, depending on what type of charger you look at, sometimes it will present 2 volts or 2.7 volts. So by providing different levels of voltage, a charger is able to specify whether it can provide half an amp, 1 amp, 2 amps, and so on. So let's get the multimeter out and plug it into these ports and see what we can figure out. So first of all, looking at the IKEA device, I have a little jig here that so I can get to the wires of the USB. So we'll just plug that in. And we'll set the multimeter to voltage. So looking at the power pins, first of all, we can see that there's about 5.2 volts on there. Now we can look at what's on D+ and D-. So that's 2.7 volts. and that's 2.7 volts. So basically signalling with 2.7 volts on both the D plus and the D minus will tell the device that you've plugged in here that there's 2 amps available, and so the iPad will switch and start drawing 2 amps. Just for completeness, we'll check whether the D plus and D minus pins are actually connected to each other. That's showing a resistance of 68k, so they're certainly not looped back to each other. So now looking at the Jackson device, let's put the meter in the view there. So I'll plug the jig in once again. First of all, we'll set to voltage on the multimeter, and we'll check the voltage coming out of the port here. That's saying 5.1 volts. So now we'll measure the voltage on the D plus and the D minus. So it's hunting around a bit on the multimeter, but that looks like 0. If we have a look at the other one, similarly that's reading 0. So basically there are no voltages presented here, there's no resistive divider in here, and therefore this is why the Apple iPad refuses to see this as a high current charger. Now if we switch to ohms now, let's measure the D plus to D minus resistance, and that's basically 0. So these 2 pins are wired together, so the D plus and the D minus are looped to each other, and this is the DCP specification. So there are smartphones around and tablets around that will see this as a high current charger and will try and draw 2 amps, but unfortunately for me the iPad won't see it and will only charge quite slowly on here. So looking back at the standard data port again using my hub, you can probably hear the rain outside. It's now raining extremely hard. So if we measure the voltage on the D plus and D minus pins, so that's reading 0. So these pins read 0, and if we measure the resistance, let's measure the resistance to ground. So that's about 20k, so there's 20k resistance to ground. And the same there. So basically these 2 links are pulled down to ground with a resistance of 20k. So as I showed on the diagram just now, this is how a device can be detected as a standard data port. And looking at the good old Poundland device, if you've seen Big Clive's video, you'll already know the answer to this because he took it apart. And so if let's leave that on the resistance setting, and we'll measure the D plus to D minus resistance, and it's 0 ohms. So the 2 of those are looped back, they're looped together. So this is supporting the DCP specification again. So in a previous video I took apart another cheap charger which also had the D plus and the D minus pins looped to each other. So I'll put a diagram of that up here. So you can see that the PCB track joins the D plus and the D minus, so they're permanently looped together. So once again, the Poundland charger will, be recognised by some types of smartphones as a high current charger, but unfortunately not the iPad. So this whole area of high current chargers is quite interesting and is set to change quite a bit further in the years to come. There are a couple of specifications to make chargers even smarter and to allow even more current to go into things like tablets. So one thing is the Qualcomm Quick Charge specification, which again uses the D plus and the D minus pins to signal, and the devices can negotiate how much voltage they want to change, not just current, but they can negotiate a higher voltage like 9 volts or 12 volts. And then there's also, in the more standards based USB, there's USB type C, which uses a much more sophisticated, rather complicated method of signaling, using some extra pins on the USB-C port, and so there'll be a lot more smart chargers in the next few years, and the world's going to get even more complicated than it is now. So I hope you found that interesting or useful, an explanation of why some devices won't charge fast when you want them to. And if you enjoyed it, please give me a thumbs up and subscribe for more videos like this.